the head has a button.
Good morning, BWSI. All right, can I have your attention? And it is time to put away laptops and cell phones again. And some of you noticed yesterday that there was one course who got to go last. That was the course who had the most cell phone time during the seminar and the most snap time during the seminar. So we do pay attention as to what's going on and what people are doing. So the class that's got the most nappers will go last. So just to let you know. As you guys noticed as you were walking in, there is pizza today, right? So there's pizza and salad. I just want to point out that right now for the first time through the line, just take 2 slices. We want to make sure we've got enough for everybody to go through. If there's pizza left over, you can come back to the line again. But just for the first go through the line, you can take all the salad you want and 2 slices of pizza. So, yeah. So, at this point, I'm going to let Bob have the microphone. Come on, quiet down.
Oh. So a couple more things. Have you all received the invitation for the final challenge? Yes. You did not? So if you can RSVP, that would be great. We'll be sending out another email, much the email form that you can forward to your friends, either today or tomorrow. So looking forward to do that. So before, let's see if everybody's here. So race car. Okay. UAV. UAV SAR. All right. Cogworks. That's good. Metalytics. Embedded security. CubeSat. Okay. 3D printing. Did I miss anybody? That's all good. So what is BWSI? All right. So today we have another great talk by Professor Darva Newman. How many of you think within the next 10 years we will send an astronaut to Mars? How many of you would like to go to Mars in your lifetime? All right. So we're going to find all about that. She's going to tell us how we're going to get there. It's a quick introduction. She's the Apollo Program Professor of Aeronautics at MIT. She was also the NASA Deputy Administrator from 2015 to 2017, nominated by President Obama and unanimously confirmed by the U.S. Senate. She received her all graduate degrees from MIT, and she received her bachelor's degree in aerospace engineering from University of Notre Dame. So with that, let's give her a warm welcome.
I'll sing.
If you're ready. Ready?
Thank you. How's the sound? Sound check in the back. Can you guys hear me? In the top row? Testing. 3, 2, 1, launch. 3, 2. I think I'm going to have to hold this. There we go. You can still hear me, right? Hello, sound people. Testing, testing. 3, 2, 1. Now I know you can hear me. Okay. All right, I'm going to walk and talk here. Bad design. All of you want to be engineers. Redesign walking mics for people who don't have pockets, like ladies in dresses. So it's a good design challenge. I'm very glad to, yeah, that'd be better. All right. Okay, so if you allow me, I'll take you on a journey. We will definitely get to Mars. The ones who voted for the 10 years, I hope so. You're optimistic. I think it'll take 15. I'm going to work the next 15 to 20 years, and then we better have boots on Mars. Okay, and I'm going to tell you about the Earth a little bit, too. So I'd love to start with this image from our Hubble Space Telescope. So raise your hand if you're 27 or younger. It should be everybody in this room. Okay, so your entire lifetime, our Hubble Space Telescope has been out in space. It's in low Earth orbit, but it's looking for evidence for these three fundamental questions. That's what exploration is all about. Are we alone? Are there other habitable planets? And what about life elsewhere in the universe? Those are our three fundamental questions that drive all of our engineering and science. So it's a beautiful image, 3 dimensions of the Wonderlist cluster. So, do you know about something called exoplanets? Yeah, a few people? Okay, well, we have 6,000 of them. So when you only had to study, the 9 planets, counting Jupiter, a dwarf planet, there's 6,000. So, you have to study a little bit more now. Now, we're looking for the ones that potentially, these are Earth-like planets. They're really far away, 10 to 100, light years away. So we're not going anytime soon with humans. But they tell us about the beginnings of the universe, how planets are formed, and we are looking for habitable planets. That was question 2. Well, there's about 24 of those 6,000 that are really interesting. We call them, they're in the Goldilocks zone. Not too hot, not too cold, just right, probably to that life could form or we could inhabit them. So we look really closely at these couple dozen exoplanets. Now, these are artist renditions, because, of course, we've never been there. Even our probes haven't been there. We just have the scientific evidence, right? It's usually a Doppler shift, how we see the evidence for these planets when they go around the sun. So every star that you see at night, especially if you live in maybe a more rural place and get out of the light pollution of Boston or somewhere, you look up, that's a planetary system. We didn't know that until recently. You look up at all those stars, well, it probably has lots and lots of planets around it. That's what we're finding out in our recent research to, again, discover kind of where did we come from in the universe. Now, maybe closer to home, you've probably all seen Star Wars, right? Many of the Star Wars movies. Well, I know Luke Skywalker, move over, because on the right you see Kepler 16b. That's an exoplanet that is a binary system, meaning it has 2 suns, so you get to see 2 shadows. Right? So it's not just in the movies. This is kind of where science fiction becomes real. This is our real science. And there's a really big effort now underway at NASA and all over the world. We always do things internationally with our scientific and engineering, our aerospace engineering colleagues. It's called Ocean Worlds. Because when we search for life in the universe, and just even in our own solar system, we say follow the water. If you want to look for the evidence and the chemical constituents that would form life, we say look for the water, follow the water. So we'll get to Mars in a minute, but there's a lot of other really great places just here close to home in our solar system where we see the evidence of water, specifically icy water, oceans. And most of them are ice oceans, but we do see water underneath the ice. So Enceladus is literally talking to us. It's spuming out. It's kind of like going to Old Faithful in Yellowstone if you've ever been. Well, that's what little Enceladus is like. It's a moon, and those are hydrothermal carbon shooting out vapor all the time. So we say, wow, could be life in that ocean. We also have a mission in the 2020s to Europa called the Europa Clipper. Europa, as hopefully you know, is a moon of Jupiter. We have a mission called Juno. It's named after the goddess of Jupiter, at Jupiter right now today, going in orbit. But Enceladus is a particularly interesting moon of Jupiter. That's a heat map up there from our recent 2014 and 2016 missions to go to Jupiter to see what the heat map is, because we look for water under the ice, and then if we can see a thermal map, maybe that would be a good place to send a lander. So there'll be a Europa Clipper mission that just kind of flies through the atmosphere. It's kind of like the chemical lab, if you will, to look for the evidence, the chemical constituents of life, and then we'd like to land on the ice. And then the engineering challenge is we have to drill kilometers and kilometers deep before we get to the water. And we don't know how to do that too well today. So that's a good engineering challenge coming up for our Ocean Worlds missions. And you can see all of these. I've just highlighted 2, but these are all the top priority space missions to go, we call Ocean Worlds, to look for life. Okay, I want to zoom in even closer in the solar system and tell you about Mars. That's kind of my favorite planet. Well, after Earth, of course, it's number 2. This is the best planet we have going. This is not option B. We'll talk about that more. Again, and you can ask me about Elon and SpaceX or Blue Origin and how we're going to get to Mars, because it's a government investment, it's a university research, and then it's a lot of the public-private partnerships, which I had the great pleasure to be in charge of all of those when I served at NASA. Over 1,000 different partnerships, and we worked with 120 different nations. So it's much easier to say the few nations we didn't work with. We worked with everybody. Again, it's very much global exploration. That's what this map kind of shows. We are on a journey to Mars with humans. And let me show you the history of Mars. This is going to be our scientific probes to Mars. And I have a video here I'd like to share with you.
Preliminary analysis of this data. Can you describe what you see on Mars?
Yes, it's there.
Really hard and it's really far away. So we practice landing. We try about every which way to land on Mars.
Make 7 meters. 20 meters.
This is
60
retro
meters.
rocket
Standing back with touchdown.
It's really cool when you land, nail a landing. It's all about the people. Look at all these people. That's the most complicated landing we've ever
Led
done
by
on
the
Mars.
extraordinary men and women of NASA and our Jet Propulsion Laboratory. Right now, the wheels of curiosity have begun to blaze the trail for human
my boss
footprints
at
on
NASA.
Mars.
I just wanted to call and say
Who's our big
congratulations
boss?
to the entire Mars Science Laboratory team and really all of JPL. You guys should be remarkably proud.
I'm going to show you some data from MAVEN. That's one of our 7 assets at Mars today. And that's our next big rover. We have an amazing MIT experiment on it. But that's what I keep thinking about. How do we make that giant leap? Now, truth in advertising, I just showed you the successful missions. Talk about that as well. You learn a lot more from failure than you do successes, but I only have 2 minutes for that video. Okay, so 3-phase plan that you see up here in this graphic. So we're on International Space Station today. We've been there actually for 18 years, so maybe as old as you guys are, your entire life, we've had astronauts working 24/7 in low Earth orbit, and it really is international. We've been learning a lot, and we've been working there together with the Russians, the Japanese, European Space Agency, that's 22 nations, and Canada. So it really is, we're all in. It's very international. But that's close to home, where we still have mission control and we do space apps. Then we move to the moon. The moon is next. In the 2020s, we move to the moon with humans because we need some more practice. It's just 3 days away. But I said we can have no dead-end elements. We don't want to invest in anything on the moon and get stuck in the moon. We've been low Earth orbit 40 years. We don't want to get stuck on the moon for 40 years. So Mars is the horizon goal, but it's really hard. We can't just get that. We can't just go today. We have to invest in the technology, so we can talk about some of those technology investments. But when we are ready, you know, when the launch window opens, then Mars is a horizon goal because it's the hardest thing we know how to do. Hopefully we'll succeed. And it's going to be governments and private money as well. It's a really great relationship between public and private. I put up in the top left, our little own adventure, we took our sailboat and sailed around the world. So we circumnavigated so we could teach students, just like you, about exploration by sea and space. Because I think living on an island and existing and surviving is very much like sending astronauts up to space station or in that really small capsule to Mars. Okay, so how do we get to Mars and what's the current data from Mars? On the right, you see our artists from JPL giving you a travel poster. So don't quite buy your ticket yet today to Mars. But I always bring in the artists because they're the visionaries. They tell our stories. They help us envision places we haven't ever been. And on the left is our science data. I'll show you a couple images. On the top left, we actually have the evidence for water on Mars. We knew that there was ice on the North and South Pole, but now we have seasonal water flow. It's very high in acidity, so you can't drink it yet, but it's just good to know we're looking for, again, life, we're looking for water. If you saw the information from Science just last, when was NDC Wednesday, a new paper just came out. We have a 12-mile lake underneath the surface of Mars. So we're getting really close. We're getting a lot more evidence for water. Follow the water, you look for life. And you see what's happening on that simulation here in the top of the bottom left. Mars does not have a global magnetic shield. Earth does. Lucky for us. Keeps life here going pretty well. Mars lost its electromagnetic shield, probably we don't know, 3.5 billion years ago. So Earth and Mars are sister planets, 4.5 billion years old each. Mars probably had life, we think, was wet, warm, maybe wonderful, but 3.5 billion years ago, something went terribly wrong. It lost its atmosphere. That simulation you just showed is data from our MAVEN spacecraft and the other flying probes we have in the atmosphere. You're seeing the solar wind and the solar radiation ablating. It's literally ionizing away the Martian atmosphere. Today, we're left with 1% carbon dioxide atmosphere on Mars. So that's why we're so interested in Mars. It's our closest sister planet that tells us much more about life here on Mars than potential past life or cold, dead life on Mars. But it tells us about climate. It tells us about atmospheres. It tells us about how do you exist and live in this solar system of ours. So that's some of the data. I say we have 7 assets on Mars today. Assets, that means the world. NASA has 5 of those. And then the Indian Space Agency, whoo-hoo, on their first trip, cheap mission, they got a probe up. It's called MOM, so I love it. It's for the Mars Observing Mission. And now Europe has one, Mars Express. And data from Mars Express, as well as the NASA instruments, just found that lake. You find that with penetrating radar. You use radar technology to penetrate below and see this lake underneath the Martian landscape. So that's some of the latest data. Again, 3-phase plan to get to Mars. First space station, then the moon, and then Mars in 3 phases, right? I'm here probably because of Apollo. Well, we had something called Mercury, Gemini, and Apollo. That's how we got to the moon, a 3-phase plan. So we rolled out a 3-phase plan for NASA. You might know about Scott Kelly. He did the 1-year mission. We're going to do more of those. He had his Russian colleague, Mikhail Kornienko, so we can study the biome, the gut, kind of NASA into genomics. We sampled DNA. He has a twin brother, identical twin, Mark, former astronaut on the ground, so we could really test Scott up in space for over a year, just under a year, and Mark down here. And we learned a lot. All the scientific data is coming back. This is kind of the specialty of our lab here at MIT. We study muscles and bones and how astronauts are keeping them healthy and well and designing suits to kind of counter all this physiological deconditioning. Mark and Scott, they're both doing well. Scott's back on ground. He's not going to fly anymore. He retired from the astronaut corps. But it takes a long time for his muscles and bones to rehabilitate. You lose about 1 to 2% bone mineral density per month. Now who wants to go on my 3.5-year Mars mission? All right, I still have some of that. That's good. That's why I love talking to students. But the research we do is we try to counter that, through suit designs and nutrition and things like that, because we don't want you to lose all that bone and muscle. And the number 1 showstopper for human spaceflight, what do you think it is for a Mars mission? Radiation. Yeah, it's radiation. So we're working on that. Radiation protection gets to the genetics of it. Maybe a few of you guys are radiation-hardened individuals. That's awesome. First, it's awesome for cancer research, but it's really awesome in my world because guess what? We're sending 4 people. I want to send you 4 that are radiation-hardened. So we got to look into the genetics and things like that. We want people to be safe and well and be able to endure that trip because it is a hard, long trip. But we're up for it, I think. I'll show you a little bit about our research that we do in my lab. We work on 4 suits, actually. And so this is one we call a gravity loading countermeasure suit. Because of that musculoskeletal loss, your muscles are you're gonna lose about 40% of your strength in your muscles just when you're on space station, because you're floating. You're no longer a biped, you're floating around, you're losing your muscle mass. You still exercise a lot. And about 40% strength loss, so we see about 30% muscle atrophy, typically on our 6-month missions, and we've only done one year-long mission. Again, Mars is 3.5 years, some in microgravity, some on the surface, and Mars is a 3 ACE gravity environment. So this is a suit that you wear inside a pressurized vehicle, and it's kind of like an exercise suit. And so it's kind of, like an athletic suit, if you will. And we load you vertically, kind of from trying to recreate basically a one body weight loading on your feet. And you're kind of exercising against that. You can look up the papers. We show you different research. It also has applications on Earth. So we take all of our technologies, our kinematics, that's looking at body joint angles, force ground reactions, and we apply those to suits, if you will, and exercise regimes for specifically pathology here on Earth, like cerebral palsy, and try to work on locomotion and motor control and extending the range of motion of people walking. Okay, let's talk about spacesuits. These are my Apollo bloopers.
No, dadgummit.
Jack Schmidt having a few problems.
Okay, that's 1/6 gravity on the moon. It's really light. You can all slam dunk a basketball, but you're not very able to walk around in a big, clunky, gas pressurized suit. So I call the current suit and the formerly Apollo suit, it's amazing. It's an amazing engineering feat. It's like a spacecraft in miniature because it has to give you air to breathe. It has to scrub out your carbon dioxide. But it'd be better if we could design them to give people more mobility and to be much less massive. So our designs try to push mobility, try to make them a lot lighter. They are engineering marvels, like I said, the world's smallest spacecraft because it's coupled right around your body. But from the bloopers, we couldn't do much science. Right? You're so worried about falling over. It was really hard. That was Jack Schmidt, the only scientist we sent to the moon. He's a geologist, and he really had a hard time bending down to take his scientific measurements. So that's no good. So we can do better. So we have a design of kind of shrink-wrapping people that you see over on the right that we call the biosuit. But first, I'll tell you a little bit more about the current state-of-the-art. This is the current NASA suit. We put it on our robot in the lab, and we test it. And it's a heavy suit. Again, it's gas pressurized. It weighs about 140 kilos. That's pushing 300 pounds. When you're in space station, it's okay because you're floating around, so I don't care how heavy the suit is. But I get to the moon and it's 1/6 G. I get to Mars and it's 3 Hg. So now I care about the mass and mobility of my suit. It's making you work pretty hard. And matter of fact, the current suit is injuring our astronauts, unfortunately. So we have 26 astronauts or former astronauts who have had to have shoulder surgery. Now, they don't get hurt when they're in space, on space station. They get hurt when they're underwater training. We train about 12 hours in an underwater swimming pool at NASA Johnson Space Center in Houston for every 1 hour on orbit. So that's a lot of wear and tear. And you see my X-ray on the top right. That's the suit bearings. We call those psi bearings, fancy names for spacesuit shoulder bearings. Well, they're metal. So can you imagine going in a swimming pool upside down against that hard metal and my nice soft, muscles and bones here? It hurts, and let alone we see a lot of injury as well because torque still counts, right? You guys know F equals ma in torque. So I'm just trying to repair the Hubble Space Telescope or something that's very massive. Even if I'm in weightlessness, the torque arm, my muscles are only so strong. So you really are putting a huge amount of torque and extra work, if you will, especially on some small musculature. So we see a lot of shoulder injuries. We see a lot of finger damage. You just kind of have to tough it out. And that's because we're working in a constrained gas pressurized suit. Keeps you alive, that's good, but it's really hard to work against. So I want to show you some of the research we do to measure the injuries, and give this data to NASA in terms of, so we invented some new pressure sensors. We wanted to make them wearable technologies, right, on the astronaut's arm and shoulders, these cool little pressure sensors. Then we put them inside a demonstration suit. This is NASA's current Mars suit. Too big and massive for me, but I'll show you the testing we did. We put IMUs, that's inertial measurement units, to track the angles of the motion, and we put pressure sensors inside to see what the contact forces are and the pressure profile. So we kind of call those hot spots. So this is, again, a made and designed for partial gravity, a lunar Mars type of suit from NASA's perspective, and we're taking all these measurements on the astronaut subject inside. Kind of mobile, not too much. This is what the students call the reverse Macarena. So I like that one. Trying to demonstrate, mobility of the arms and whatnot. All right, the smoke didn't happen. That was my students editing. So what do those pressure sensors look like? If you can see this is kind of data from that run. I'll play this video for you. There we go. So you can kind of see where the hot points are, we call them. Forearm, lower forearm, and then these are all pressure profiles, and that goes from 0 to 60 kilopascal, if you can see that down here in the front. You don't want anything 60 kilopascals. That's a hot pressure, but you wouldn't want that pressure. That's too high, might cause injury, and you can see kind of some of the peak ones there. So we map the whole arm in motion. It's kind of like the eyes inside the suit, because NASA didn't have any of this data because we didn't have measurements. So this is kind of where wearable technologies and data goes that we can help them for future design of suits. Predicting injury, but also just having that pressure profile, if you will, of the person moving inside the suit. Because I move my arm, then I hit the hard suit, then I have to do a whole bunch of work to move the suit. So we kind of map that out in great detail. Okay, then we get to the fourth suit I can quickly mention, and that's what we call the biosuit. But we took some great ideas from early work in the 1970s. There's a fun little video to show you. That's a space activity suit, and Dr. Paul Webb threw that on an Air Force test sublet, and look at how mobile he is. Now, this is before spandex and Lycra and things like that, where we could really have the right materials. So this was supposed to be, a second skin suit. Can we apply pressure directly to the skin, give you more mobility, rather than putting you in a gas pressurized shell? So I thought this was a great idea just way before its time, because this is the 1970s. Now, this is why NASA didn't continue it, because you couldn't dress yourself. We call that donning and doffing in the spacesuit world. If you can't put on your clothes and take them off by yourself, that's a problem, because you're not going to Mars with many people. And we don't want to waste your buddy's time having to dress you and undress you. And so the reviewers, the spacesuit reviewers, are saying, hey, that looks like a leotard for a two-year-old. But again, they didn't have the materials that we have today. So I'll show you a little bit of the research that how we've improved upon this design and come up with our latest designs. A little bit of math here. What we do is I'm trying to minimize any extra work. I don't want you to have to work against the suit. That's what you have to do in the gas pressurized suit. So if I can have delta W, that's work, and drive that to 0, how could I do that? Well, I think I can do it through this design, okay? Because if I can put the fabrics and the pattern right on your skin, then I want to give you maximized mobility. So that's what we're trying to do there. We're trying to minimize any extra pressure work, and WE is then, you can look at the strains and stresses in the material design. Again, we're trying to reduce that, not make you do any extra work to overcome the suit. And then you can deal with material properties. So you see kind of stress and strain up there in my equations. And again, trying to minimize the work. And then what you see in the little animation, the circles, put circles. If I put circles all over your arms and legs and wanted you to move, which my graduate students have done that, even our undergraduates, and basically kind of tattoo on these circles. And if you move, go ahead, move with me. Matt, you have all these little circles. Freckles work pretty good too. Take a look at, and that circle is going to turn into an ellipse. And there's going to be only one pair, but there's going to be a pair of those two red lines. Those are their bisecting, those two bisecting diameters, the two red line. Well, that pair goes from the circle, it just pivots. It didn't extend. It just pivoted to go to the ellipse while I gave you maximum range of motion. And then you literally connect those dots. It's called three-dimensional eigenvector analysis in mathematical terms. And voila, I end up with a Spider-Man suit. But it's all math. It's all elegant math. And we end up with this really amazing design of these suits. That's called lines of non-extension. Now so they literally mean it doesn't extend. So that's a really good place. I call it a soft exoskeleton. That's a really good place to put my electronics, to put my sensing. How's your heart rate? Put all that, because that line is not going to extend. Now, orthogonal to that line, it's going to stretch a lot. So skin is very anisotropic, meaning it has different properties in different dimensions. So it's really stretchy in this dimension. It's not very stretchy in this dimension. So this is the math. We don't know if it's biologically real yet or relevant to how cells lay down your skin cells, but I don't know. Maybe we'll get a big prize someday if it's biologically relevant. So we map you and we put you in laser scanners, and we look at your skin stress and strain. That's what these colored maps are here. Because at your joints, at your elbow and your knee, go ahead and stretch. your whole kneecap is stretching. The skin over your knee is all stretching. There's no lines of non-extension. In that region, you stretch, and you stretch about 40%. We have about 40% strain region there. And the back of your knee, where your skin kind of folds up and you have those tendons, that's about 20% in compression. So that's blue up there. So again, kind of that blue and orange maps. These are strain stress maps of the skin that we take from multiple subjects, so we can design you your own biosuit, because they're very much custom designed. And this is our latest technology in digital image correlation. The laser scanning and the motion capture weren't quite, we could only get centimeter accuracy. Now we can get millimeter accuracy to make the patterns that you see before you in these animations. So we map the skin, and again, we look at the elbows and the joints, because those are the difficult places. This is pretty much a cylinder, so this is easier to model or design for. But my joints are the hardest ones. So we get these skins. Now, the final piece of the puzzle is the research continues, and we need to put in active functional materials, because I can say the material properties, what I need. I have the patterning of the suit, but guess what? No one can make us a material. So that's why we work with Bob and the folks here in terms of functional fabrics, because I know the material properties, but now we have to make, in the future, if we really want to prototype and make these suits, we have to put in those active materials so that we can put those in. They're kind of like smart zippers. It's a mechanical counterpressure suit, so it needs to apply 30% of an atmosphere. That's 30 kilopascals. 30 kilopascals. We can do that, it looks technically. 20% comes from passive elastic materials, and we need to add about 5 or 10%, or in this case, kilopascals, to kind of have active materials. I call them they're basically active zippers, kind of cinch it up. Put something that's tight on, but we need to cinch it up to reach a third of an atmosphere. That's the amount of pressure you need to keep an astronaut alive. So we're moving on in the future to think about how do we incorporate these active materials. Shape memory alloys work. That's our best candidate right now, kind of designing that's nickel titanium. They're sometimes known as muscle wires or artificial muscle. So that's one of the best candidates now. It has pretty similar properties to real muscle, but it takes a lot of voltage, takes a lot of power to actually activate them, and they're kind of slow. So that's where the research is today. This is kind of hitting our desired requirements for a suit. Oh, and the final piece, I'll tell you a little bit about, we're putting in augmented reality into the helmet. This is our new helmet design, but we really want to change how science is done, and we're actually doing this today. So I'll show you this little video about science operations. We simulate this out in the field. We were just in Hawaii, where that volcano is going off. Lucky we were there in November, because our site is now under lava. But we did a lot of good geology, and we took our astronauts out, and we put augmented reality. Oh, this is maybe my, maybe that video is not working. Well, I'll just tell you about it. It's JPL software called OnSite. You can jump on the web and look at the OnSite. Right this summer, we're trying to use it for ocean exploration, because a lot of people haven't been, I'll take a poll. How many people have been to the ocean? We're in Boston, so you've probably been. Okay, everyone's been to the ocean. Most people have been to the ocean. How about scuba diving, or gone down in the water? It's fewer, so we want to give everyone that experience. Not everyone's fortunate enough. I'm a scuba diver myself, but wouldn't that be cool if we could give kids all across, the nation, what's it like to go explore underwater and see the fish and the animals? So that's what we use augmented reality for. We use it on Mars every day in real life. The 8 a.m. telecon is we put on our Microsoft HoloLens, and I talk to scientists. We have 40 scientists to date, and we talk to them about, we have one rover, right? And that's Curiosity, and it has a camera, but what image should we take to search for life, the evidence of life? So we're right now in Gale Crater. That's an old dry lake bed. We think it was a lake. We have evidence it was a lake, and we're taking a look at the geology so we can take a look. If you only get a few pictures a day, you want to have the scientists agree and the geologists agree on which image you take. So that's how we use augmented reality today. Every night we stitch together the high-def images from Mars, and then you wake up in the morning, and you get to talk to your buddies and figure out where you were going to send Curiosity that day. So that's it. The future is here in terms of using this technology for our space missions. And again, we're using it for Earth missions. And I want to end my talk just showing you this beautiful planet. Like I said, Earth is the best. We have a lot of low Earth orbiting satellites, 20 of them, matter of fact, and they're pointed eyes down on Earth. So we're taking a look at the oceans, the land, the air for climate, and we have these big supercomputer simulations. Here's some of them. So if you want to know about soil moisture, you want to know about sea temperature rise, if you want to know about all kinds of things about climate and the Earth and all of our systems from oceans, land, and air, we take the data from space. We also fly aircraft. I'll show you a little bit of that data. I call them the Earth's vital signs because the Earth is definitely speaking to us. I'm just not so sure we're listening these days. It's pretty important. Here's some of our data. We've increased by 1 degree Celsius. This is globally since 1880. Can you see that year up in the top right? It's kind of small. Raise your hand when you're born. Okay. We're only in 1910 now. Blue is 1 to 2 degrees Celsius below a running average of 30 years from 1950 to 1980. Yellow and orange are 1 to 2 degrees Celsius above the mean. Okay, 50, oh, so there we go. Thank you, Bob, for playing. Yeah, thank you. Here's our generation, the baby boomers. Here's your folks, okay, 80s. When are you guys born? 90s? All right. Got some of the TAs born. Whoa, there we go. All right. Well, guess what? It's hot. That's your lifetime. That's mean average in your lifetime. So we need to think about that. Let me show you the carbon dioxide in the world. We just hit 410 parts per million. We don't want to be at 410 parts per million. We don't even want to be at over 400. Yellow and orange in this three-dimensional run is over 400. Blue is under 300. That's where we'd like to be. Take a look at the northern hemisphere. This is 1 year of life in the carbon dioxide cycle. This is from 2014 to 2015, and I'm showing it to you in 5, 10, 15, 20 kilometers up. This is the literal definition of trapped greenhouse gas. This is carbon dioxide. This is human-made and from our forest fires and other things. So we have a choice about these emissions. We have a very conscious choice about how we want to live our lives and what we want to do. But we just went over 410. And as I said, that's trapped greenhouse gas. Hence, the temperature data. Our oceans are absorbing as much of this carbon dioxide as they can. They absorb 30% of it, but that's about all they can do. And so again, this is kind of some of the Earth science. And finally, I'll show you Greenland and Antarctica. When I was at NASA, it was on my bucket list. Got to go to Antarctica twice, actually. Fly over Western Antarctica to measure our glaciers and to see how they're melting. And then I got to go to the South Pole. So there I am on the South Pole. It only takes 3 seconds to run around the Earth, to run around the world. This is really cool. It's really fast. It took us 18 months in our boat at 6 knots, so that was a little slower. And iPhones do not work well in South Pole, just saying. I brought 2 just as a backup, right? And they froze within seconds because we were at 30 below, and that was a hot, balmy summer day. The day before was 60 below, so we were 30 below. Anyhow, thank goodness there were some other photographers there with better cameras. And so Greenland and Antarctica hold 99% of the world's fresh water trapped in our ice sheets. So let's see how they're doing. This is taking a look at a vector, a mathematical velocity flow of Greenland's ice sheets. If the Greenland ice sheet, it's melting, but if it melts in its entirety, that would be 6 meters of sea level rise. The last 20 years, we've had, 2 decades, we've had just over 20 centimeters. So we've had this sea much rise globally. So you can take a look at that simulation. We look at it, it's not that it's just melting, it's melting really quickly, and we need to know the velocity that it's melting as well as the surface area. So we lost 287 gigatons last year. That's 3 times the size of Texas is how much ice we lost out of Greenland. So that's not a good story. Antarctica, we lost 125. Now, Antarctica is a 10,000-foot continent, almost all ice. And it's also surprising how much we're losing. Again, this is, we need to measure it and monitor it, but I think it's much more important to have people act in terms of what kind of Earth do we want? What kind of life do we want for us, for our children? The reason that a space woman cares about this is I spend my life trying to get people to Mars, but we have a very transformative and interesting perspective. When I look down on Earth, this is what I see, this amazing, beautiful planet with that glow. That's our atmosphere. And if I shrink Earth down to the size of a basketball, then our life support system, what separates us from Mars and every other planet that we know about, that's only 3 human hairs thick. to the scale of Earth down to a basketball, that's how precious our life support system is. You see it, when you're in space, and it's beautiful, but also is transformative in terms of you think about, okay, maybe how fragile and precious this is as well, and we better take care. And I argue that it's for the world. It doesn't matter that I'm in the U.S., and it doesn't matter if I'm in Russia or I'm down the bottom of the world in Antarctica. We all need to take care because we're all in this lifeboat together, right? Really isn't an option B. Okay, so that gets us to, what can we do about it? You probably know about the Paris Accord. I hope you know about the Paris Accord, COP21. We've already had COP22. There were commitments made. And the good news is that there's tens of thousands. There's the actors, the good actors are people, just like you and me, doing what they can in their cities, doing what they can in their states, doing what they can in their nations. So the world is in. We won't make this political, but the world is in, and in the U.S., there's a lot of cities and states and regions that are doing what it needs to take to get this done. And it really is urgent. That's why I take the time to show it to you. Our part is we actually have an effort called Earth Speaks. Want to show people the data that I've just shown you, want the Earth to speak to all of us in whatever way it speaks to you, and then for people to say, okay, how can I act? What solutions are there? How can we move forward? So Earth DNA is actually our nonprofit, Earth Speaks. It's it's kind of an artificial intelligence platform where we're curating the data, visually presenting it, so that people can see it, can understand it, can use it for their own means. And it goes across this. We've specialized in the oceans so far, and it goes from the global, regional, just to solutions anyone can do, at home. I can tell you more about that. I talked a little bit about us sailing around the world. It was fantastic. We survived, taught thousands of kids all over. So I came back to being a professor after we survived. There's a lot of beautiful places around the world. You only take pictures on a really beautiful day. You never take pictures in terrible storms and when the seas are, 10 meters or 30 feet high and you're worried about if you're going to survive. And then my last slide and message to you is here. I spent my whole career in STEM. How many of you guys are going to major in STEM? Science, technology, engineering, and math. Okay, I love you all. I know who I'm talking to, right? I have the STEM crowd here. But I've actually changed the conversation. And so I'll just spend, my last 30 seconds on this. I call it STEAMed. I always bring in the artists, the journalists, because I talk about going to Mars a lot, right? Well, I'm a technologist and a geek. But it's the visionaries and the storytellers and the historians that tell me where we've been and how we're going to get there and paint my pictures. And I put D on it. That's for the designers, because there's a whole generation. All of you guys that are in 3D printing, you're in this summer session. Y'all get to 3D print? Yes? You raise your hands. Raise your hands. All right, there's my 3D printers up there. Well, you're the designers, so I want you to be an aerospace engineer. But if you're not going to be an aerospace engineer, then all designers are in too, right? Because we don't have the luxury to weed people out, to filter people out. So if you go back to your classes, you don't have to be the best in calculus, math, and physics. If someone's telling you that, I say it's bunk. I use those tools every day as an aerospace engineer. Those are my tools. But I didn't have to be the best in the class. They're just tools, right, that I could use as an engineer. So we need to filter everybody in. That's my story, is we need to filter everyone in, and especially if people say, oh, STEM, that's not for me, because that's kind of this intimidating thing over there. Then we had the wrong conversation. The conversation is, you want to get people to Mars? Do you want to solve clean water on Earth? Do you want to work on climate? Those are big problems. We need everybody, and we need all disciplines. We need all disciplines. So I call it STEAMed to make sure that I'm having the right conversation with people. It takes the artists and the scientists, it takes the designers, it takes the engineers. And I think if we look at our big challenges for humanity, we need everybody. So I'll end with this wonderful image. Everybody know who that is? Who's that up there on the top left? That is Katherine Johnson. You guys don't know Katherine Johnson, a mathematical, yes, someone up there. You've seen Hidden Figures? Read the book. Read the book. It's really great. It's a great movie, and maybe Pharrell said it best.
Don't you know that we're able, and that alone makes us major? We can all sit at the table.
So I'm here to tell you that everyone's in. Go recruit your other, high school buddies. We need everybody. We have these great, wonderful challenges to solve. It's been a pleasure to talk with you. I think we can have some Q&A, and I know you get pizza as well. There's a hand way up there in the top.
So your suit design that you were talking about, considered making like an autonomous dresser?
Bring a robot dresser up there? It would be good. We thought of a little bit of a version of that. So, in donning and doffing, that's why we actually use the active materials. Because I can use passive in our designs. That was 1970s. They had trouble dressing and they didn't have the right materials. Now I can, put my arms and legs in. It's pretty tight, but I can dress myself. And then how we're trying to solve that is with the active materials. You push a button and it cinches up and gives me that extra 5-10 kilopascals I need. Because if we had an autonomous dresser, the thing we thought about it is we're taking a suit that's tight and making it tighter. If you could reverse that, the ideal would be like a reverse vacuum. So if I had the suit and it was in a vacuum and it was big, and I jumped in it, and then when I took the vacuum off, it would shrink wrap. That's as far as we've gotten to like autonomous dresser would be what would that contraption look like that would actually make it too big. And we, in the serious part of that technology development, we looked at shape memory polymers and things like that, biphasic materials that you can study and learn biphasic. So it's a little bit bigger this way, and then you do something to it chemically or electrically or mechanically, and it has a different shape. So that's as far as we've gotten on the autonomous. Our robots aren't too good that we send to space right yet. We're trying, but they're pretty, they're kind of old school. They couldn't dress anyone yet by a long. They have about 1 to 7 degrees of freedom is all we have right now with our current robotics in space.
That it has a lot of insulation, so for extreme temperatures, but how, or other planets, how does the thinner suit take problems? How does the thinner suit solve the problem?
The thinner suit. That's a great question down here. It's about thermal control, about the suit. So for the biosuit, when I showed you, that's a pressure layer. What we focus on is a pressure production layer, because that's how you keep someone alive. The thermal layer, I don't have my little samples here. Basically, it's kind of like we'd solve that differently. We would decouple that. Right now, the current suit puts all that into 14 layers, and that's why all suits are white, because they have to reflect emissivity and absorptivity. So that's why all suits are white with some stripes on them. But basically, for us, it's kind of like going skiing or going to Antarctica. When I went to Antarctica, I had to load up and load up. It's kind of like getting dressed for space. You just keep putting on layers. And so we think with some really nice thermal aerogels or really, some really interesting materials, but you would put a coat over that. What you saw in the biosuit, that's the pressure layer, and you would need to put your thermal layer on top. We have wires running in that we've tested. We can heat you up and cool you down about 5 or 10 degrees Celsius, so that's just for comfort, for thermal comfort. But when you're out in vacuum, when you're even in low Earth orbit, 200 plus to minus 200 on the moon Cs, you have to have, a major thermal garment. All righty, who else? Red shirt.
Maybe 15 years before we get a man on Mars, and you said 10 years is optimistic, so why do you think it will be 15 and why is 10?
Good. So if everyone heard the question, when are we going to get people to Mars? So we are on this plan. It doesn't have too much to do about our technology. How many saw The Martian? Yes, everybody saw The Martian. It was awesome. I got to open it when I was at. So we signed what's called a Space Act Agreement, and Andy Weir wrote a great book. The book's even better, and Ridley Scott made a great movie. They wanted it technically sound, but if you remember the technology's in there. So what's it going to take to get humans to Mars? Right now, from my movie, I showed you all those successful landings. All I know how to do today is land 1 to 2 metric tons on the Martian atmosphere, 1%, and given the gravity environment. So a human mission, and NASA specs it out as 20 to 40 metric tons. Whenever they're saying, no, modular design, we teach systems engineering here, we have to ramp that up. 5 metric tons, 10 metric tons, even if it's modular, a human mission is order of magnitude more than what I can do today, 1 to 2 metric tons. It has to do with entry, descent, and landing. Entry, descent, and landing, since Mars has an atmosphere, it's so small, 1%, it's just a darn nuisance, because it's not big enough atmosphere to slow you down, but it heats you up. So you need your heat shields and things like that. So that's technology we really have to work on for Mars. We have to work on life support systems and suits, but your entire life support system, we have physical, chemical life support systems on space station today. The loops are not closed. The air loop, we can recycle the air and the water, but it's like 65% closed. We need to get to 100%. The water loop, we're about 95% closed in the water loop. That's pretty good closure for the environmental closed life support system, but that's old technology we're dealing with today. So we do really need new technologies in life support, suits, propulsion. We need advanced propulsion. right now, maybe with chemical rockets and heavy lift, Space Launch System for NASA, Elon's big vehicle, heavy lift, might be able to get there. And Blue Origin has some great engines coming up. The BE-4s are incredible. So we're going to have heavy lift launch capability. Lucky for us, we haven't had it since Apollo days. We haven't had it for 4 decades. So really looking forward to heavy lift. And radiation, when it comes to the humans, these are all the technologies that are going to take. We're investing, but I wish the investments were more to get at 10 years. So I think we'll probably have launch. We'll have launch capability for sure to get us in Mars within 10 years, the people who voted for 10 years. But we have to have all those other systems come on board. And probably should go to the moon and test them out. Again, I call it no dead-end elements. We don't need to be going to asteroids with people. That's silly. On the moon, we don't want to get stuck on the moon. There's some resources on the moon and things like that, but really, if we have focused investments in life support, habitats, we need smart habitats, deep space habitats, because again, right now, everything is within low Earth orbit, and we're within the Van Allen belts. So radiation environment completely changes when we go into deep space and get to Mars. So those investments, and then you look at orbital mechanics. We'll keep sending our rovers, and we'll be on Mars all of the 2020s. The world will with orbiters and rovers, but we have to, there's about 8 or so technologies. I just listed about 5 of them, and you saw some of those technologies realistically displayed in the Martian. It won't all be potatoes. We need bioregenerative life support. All successful exploration has lived off the land, so we have to figure out how to make the habitats, and it's a lot of basalt. So the challenge for all of you smart folks is that I don't get to send my 3D maker to Mars. The maker has to make itself. So we truly need a replicator machine. Make the maker out of the basalts, because you don't get to take all that mass with you. I have one asset, that lovely Curiosity rover. So we have quite a stretch. When I landed McMurdo Bay in Antarctica, I've been studying space my whole life and thinking about how to get people to Mars. And I was overwhelmed. It's cool to be in Antarctica, but the reason I was overwhelmed, I looked around. We've been in Antarctica 50 years. There's just a ton of mass. It's a lot of mass. There's bulldozers and, bobcats and this and that. And I'm saying, I got nothing on Mars. And here's all this equipment. And that's how humans live, in remote environments. So that's why I'm hoping, if it's in 10 years, I'd be the first to celebrate. 15 to 20 is realistic, but we have a plan. We have to make the investments. I don't want it always to be 20 years. I don't want you to be up here talking and saying, yeah, guess what? It's still 20 years out when you're my age, That's the problem. Okay, let's move over here. We haven't gone on this side, right there.
On Mars to come back?
Yeah, the question is yes, round trip for sure. One-way trips don't make any sense at all. You are really going to miss your family, and you want to come back to Earth. Again, it's planet Earth. It's the best thing we have going. So I love going to Mars for exploration, maybe even setting up. But again, it's exploration. We might set up if we get people there. It's not going to be massive thousands and millions of people anytime soon. So all of the government investments for sure, and it gets to the ethical and the moral issues, you have to invest. You want to keep people alive, and you do want to, it's always a round trip when it comes to governments or I think more sane plans. None of this one, even though a lot of people would volunteer for that one way, I don't actually think it's ethical. Okay, we haven't been over on this side.
All right, so this is going to be like a pretty big what-if question, but let's say, what if, it was actually like a kind of civilization on Mars, like colonies and such. What powers do you put you control the colony? Would it be an independent government? Would it be Okay.
It's a good question. It's a good question. I got it. So we're going to be on Mars, and there are going to be people on Mars. How is that going to work? It's a really important question. I had the privilege to run MIT's technology and policy program here for a decade, and this is an exact technology and policy question. You're an engineer. I'm an aerospace engineer. You can be a scientist. It's really never about our technology. That's what I learned in Washington. I knew that before, but I guess you had to go there and find it out. It's about these big questions. How are people going to live together? How are we going to get along together, right? So it has to do about leadership, team dynamics, and his question is more about real big level policy. So at the UN, United Nations level, we have the Committee on the Peaceful Uses of Outer Space, COPIUS. So that's the big governing body for all space activities. We have 85 nations, so that's really who governs the use of outer space. We have an outer space treaty to use space for peaceful purposes right now. You can kind of look and there's lessons learned from treaties for the ocean. And there's actually a treaty for Antarctica, because Antarctica is kind of one of the best examples we have on Earth that is multicultural, multinational, and no one really owns a piece of Antarctica. So we kind of think that Mars might be like that. We have some of these good examples, but then of course people play around the edges and they nibble off and do things, right? If you go take a look at a map of Argentina or Chile, any Argentine and Chile map will show a big piece of Antarctica that's Argentine or Chilean, and they are raising families on the peninsula of Antarctica. And so we talk about it as a world and things like that. What are the proper, appropriate kind of global uses, not just for exploration, but then it gets to exploitation and rights. Okay, do we have? I haven't gone over here. Right here in the front.
I don't know if you're the right person to ask about this, but my bio teacher once told us, for like various reasons, but the gist of it was that like we're trashing the Earth. She said that in 3 to 4 generations, only 0.1% of humanity will exist, and that sounds like really crazy and insane, but.
Yeah, so it's a question. Yeah, so it's not primarily, but the question is about life on Earth. I care a lot about it. That's why I've turned half of my time into earth sciences and sharing NASA data. In terms of biology and how we wipe each other out, how we wipe all of us out, right now we're definitely depleting our food sources for sure. And climate has a lot to do with what you eat and, your footprint and our carbon footprints and things like that. So at the 1% of us, we do have a serious overpopulation. There's a lot of genetics. Can we make enough food for everybody as human population goes up? These are all the trades. I don't have the answer for sure, but it's fun to run the numbers and take a look and say projections and say here's where we're headed. And when it comes to climate and this data, I know much more. And how do we turn it around? How do we, we won't be around very long for sure. People have 2,100 predictions. But what I worry about is your generation and the next generation and the next generation. And, what's Earth going to be like for you guys and climate and food and things like that. So it really is quite urgent that we have the discussion and then come up with solutions. And I think there's some easy individual solutions, and then there's some levels at the government level that we need to talk about as well. But we can do a lot just as individuals. We can just do a lot as individuals. So I'm optimistic. I showed you the data not to scare you, but I want to remain very optimistic about it because that's a good thing, being an engineer and scientist, is we have the data, we're going to arm with the data, and then we can come up with solutions. That's what engineers are. We're just problem solvers. So one more question. Okay.
So, what will people do once they have landed on Mars? I mean, one way to look at it is that, if you're stranded for a very long amount of time, no period of time, so being stranded and staying on Mars.
So the question was, what are we going to do when we get to Mars? Well, there's different architectures and mission strategies. You could go for 30 days. I don't think that makes much sense at all if it's government money, because that's a lot of investment. That's a really big price tag. So you have the option that with the same, getting out there, it's going to take about 8 months to get out there if we use conventional propulsion. And I think we should stay for 500 to 600 days. What are we going to do? We're looking for life. We're looking for past evidence of life, if we haven't already found it with our rovers, because the first human mission to Mars, I just testified before the Senate last Wednesday on this, the very first human mission to Mars, say with 4 people, modest crew, we will surpass, we will go tens of kilometers. I hope we can go 100 kilometers if we have a rover or nice suits. That's more than 50 years of my video. We've been on Mars 50 years, and we've only done 75 kilometers, all of our rovers so far. So the very first human mission will surpass in terms of range, plus you're bringing your supercomputer with you. So that's what we're going to Mars, is look for the evidence of past or existing life, and that helps us learn about Earth, and it helps us learn about all the planets in the solar system. So we'll be busy. I'm not going there to sit around. What's your name? Claudia. Nice to meet you. Hi.
right, BWSI students. The first class being dismissed today is 3D printing.